Alright, this presentation is about energy and electrons and combining the two equations, the speed of light equation and the energy versus frequency equation, also known as Planck's constant equation. So the photoelectric effect says that it refers to the emission of electrons from a metal when light shines on the metal. And quantum of energy is the minimum quantity of energy that can be lost or gained by any atom. So both of those words you're going to see later. So I'd like to have you watch this video clip that's from our textbook. It explains a photon.
The energy of a photon is equal to the product of Planck's constant times the frequency of the photon. 93.7 megahertz is a common radio broadcast frequency. If we substitute 93.7 megahertz into the equation, we get the energy of the photon. This equation can be looked at differently by using the relation. The frequency of the photon is equal to the speed of light divided by the wavelength. This means that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength of the photon. Blue light has a shorter wavelength than red light. From this relation, we can determine that blue light is more energetic than red light.
Alright, so what you saw, or what we're going to look at, is the hydrogen atom line emission spectrum. And it'll show you that the lowest energy state of an atom is in its ground state. And when an energy or a quantum is at a higher energy level, that's called the excited state. So your ground state is where you start, and as you add more energy, you move up to an excited state. Alright, so what we're going to be looking at are emission spectrum, which is where you shoot a light at a slit, and the slit of light allows only a minimum amount through, and then it hits a prism, and it causes the light to be stretched out so that you can see the specific colors of the that particular source of light. So we're going to see hydrogen, and it has 4 color bands in its line emission spectrum. Here is a picture of what we're going to see, and I will go back to that. You can see that there is a purple, a blue, a teal, a green, and an orange. Sometimes the purple is harder to see, but you always see that specific fingerprint of light, those colors, for hydrogen. And each element will have its own unique set of bands, and they will be in different colors. Okay, and Bohr proposed that the hydrogen atom model that links the atom's electron to photoemission, and he decided or indicated that the electron can circle the nucleus only in specific paths called orbits, and in order to reach that particular orbit you needed to have a certain amount of energy, and to go to a higher orbit you needed more energy, or to go to a lower orbit you needed less energy. So here is Bohr's model, and we've looked at this prior. The first energy level can have 2 electrons, the second shell can have 8 electrons, the third can have 18, and then successively they have 18 or more. Alright, so I'd like you to watch this component from the textbook as well.
In the late 19th century, scientists observed that a characteristic lavender light was produced when a high-voltage electric current was passed through hydrogen gas. When the lavender light was sent through a narrow slit, then through a prism, it separated into distinct lines of different colors. In 1913, the Danish physicist Niels Bohr proposed a model of the hydrogen atom that explained atomic spectra. The Bohr model introduced the idea of quantized energy states for electrons in atoms. In the Bohr model, the electron moves in circular orbits about the nucleus. According to the model, the electron can circle the nucleus only in allowed paths or orbits. When the electron is in one of these orbits, the atom has a definite fixed energy. While in an orbit, the electron can move to a higher energy orbit by gaining an amount of energy equal to the difference in energy between the orbits. When a hydrogen atom is in an excited state, its electron is in a higher energy orbit. When the atom falls back from the excited state, the electron drops down to a lower energy orbit, and a photon is emitted. The emitted photon has an energy equal to the energy difference between the higher energy orbit and the lower energy orbit.
And so as the electron moved from the second orbit to the first orbit, the light given off would be this red band. And if you had a drop from this third ring down to the first ring, you would have that green band. So let me show you that. Alright, so here is a more complex diagram, and this is also hydrogen, and you can see that the light given off from the fall from the higher excited state down to the ground state is red here, it's aqua here, and it's violet in these two other places. Okay, so depending on the ground state of the electron and the excited state's difference is what color you get, and the light being given off is an emission. Okay, emission is emitted colors that you see. Here's another diagram of what's going on. In this case, we have the energy going into this electron here, and it rises or it goes to the excited state of a new energy level. And in this right side, you see an electron falling down to a lower energy level, and it's releasing that amount of energy. Alright, so there are two different types of spectrum that you can deal with in science. You can see an emission or an absorption. So the ones that you see with the spectroscopes are emission, and that's when energy is given off as the electron falls to a lower level. For an absorption, that's when the energy is taken in. So now you can link up the two types of equations, and you can calculate energy, wavelength, frequency, all with the speed of light and Planck's constant.